In this video, we introduce our work SceneLoom, communicating data with scene context. In data-driven storytelling, such as data videos and journalism, real-world scenes and data visualizations are two foundational visual elements, each contributing in distinct yet complementary ways. Real-world scenes, images or footage of environments, events, or activities, provide spatial and temporal context, evoke emotion, and offer visual cues that inform the design of visualizations. Data visualizations translate abstract information into graphical forms that reveal key patterns and insights. However, these two modalities differ in fundamental ways, such as the content they convey, concrete versus abstract, how audiences perceive them, immersive versus analytical, and their communicative goals, emotional versus logical. We identify three primary challenges in their coordination: modality divergence, the complexity of narrative-driven coordination, and a knowledge gap in AI-assisted design reasoning. To address these challenges, we introduce SceneLoom, a vision language model-powered system that bridges the complex design space between data visualization and real-world imagery. Guided by narrative intent, SceneLoom generates contextually expressive design alternatives, enabling seamless coordination between data visualization and scene context. We first conducted a formative study to explore this problem. From 243 real-world videos, we filtered 54 cases that combine data visualizations and real-world scenes, and analyzed their design elements across two dimensions, visual and semantic. From the visual perspective, we applied a three-step framework: spatial substrates, graphical elements, and graphical properties, to analyze data visualization components. For real-world scenes, we examined elements represented as points, lines, and planes at different levels of granularity. From the semantic perspective, we considered both the data content and the semantic meaning of entities and scene descriptions. After defining the design components, we discussed coordination strategies in terms of visual alignment and semantic coherence. Based on the decomposition of visual elements in data visualizations and real-world scenes, we proposed mapping methods to maintain shape similarity and layout consistency. Semantic coherence was further analyzed through two lenses: the binding relationship between data and entity objects, and the correspondence between data content and scene information. Through expert interviews and discussions, we refined the design space and identified additional requirements for the workflow and interactive system. The overall workflow consists of three main stages: data preparation, visual perception, and reasoning and mapping. From user input, we extract features from narrative intents, generate data visualization, and filter real-world image elements. To bridge human perception with AI understanding, we encode key design space dimensions into structured specifications. SceneLoom then maps designs through a reasoning process that integrates spatial organization, shape similarity, layout consistency, and semantic binding, including adjustments to visualizations for better integration. Finally, we evaluate design alternatives by data accuracy, visual clarity, and saliency, helping users refine outputs. Built on this workflow, our prototype system features three views: input view for data input, creation view for presenting data visualization alternatives and image inspirations to assist in selecting design solutions, and editor view for fine-tuning and rendering final dynamic outputs. We demonstrate the system workflow and results through two detailed case studies. In case 1, after uploading the relevant materials and aiming to compare the trends of tree cover decrease and increase, we generated a series of data visualizations, including bar charts, line charts, and scatter plots. Guided by image inspirations, the user selected design elements resembling straight bridges for creative exploration. After reviewing the evaluation feedback, the user chose a design combining symmetrical bar charts with bridge imagery for further refinement. As this alternative involved no data conflicts, the user skipped the refinement stage and directly generated the final animation. In the second case study, SceneLoom handles data conflicts. Following data processing and exploration of the design alternatives, the user selected a design combining raised hands with a bar chart. The system further suggested a refinement to resolve existing data binding conflicts. The user accepted the suggestion and proceeded with the refined design for further adjustments. Ultimately, SceneLoom produced a dynamic output in which each bar in the chart corresponded to an individual raised hand. Thanks for your watching.